I'm Dr. Jennifer Moses, and today we're going to be learning how to use PSPP to look at z-scores and distributions. As a reminder, PSPP is the free open source version of SPSS. Also, as a reminder, PSPP has two different views. It has what is called data view and variable view. Here is an example of data view. And then variable view is when you can actually look at all of your variables. As a reminder, a variable is a way that observations can be different. I'm a psychologist, so for me, observations are people. Height is a way that people can be different. And in PSPP, each column is a separate variable. So here in this example, I have height and weight. And then here are my various people. Also, as a reminder, PSPP has a bunch of different analyze options, graphs, utilities, transformations right here at the top. Today we're going to be using the analyze feature again. So you're going to click on analyze at the top of your PSPP program. And today we're going to use our frequency options to compare our raw variables to the standardized variables we learned to create last time. So last time we had created and saved both z height and z weight. So if you're a little fuzzy on how to do that, please go back and watch the PSPP Guide 3, where I taught you how to create standardized variables. But today we're going to use those standardized variables from last time and use the frequency command. So we're going to go descriptive statistics, frequencies this time, and we'll see a pop-up window that looks like this. And because I have some saved standardized variables, I'm going to choose the raw variables of height and weight. And I'm also going to choose the standardized variables that I made last time, height and weight. And then I'm going to click on charts and frequency tables to look at my options. I'm going to choose mean and standard deviation again for the statistics that I want the output file to show me. And I'm also going to click on charts and frequency tables. Here is when I click on frequency tables, some of the options that I have. I'm going to choose always display frequency table, always show all the cases. Sometimes you can tell it, don't even bother giving me a frequency table, or you can say, I only want to see cases that have a certain number. You can specify that, but I'm going to choose always. You can also decide if you want the frequency table to go in ascending or descending value, or from ascending to descending frequency. But the most common and most, I would argue, intuitive way to look at a frequency table is an ascending value going up. You can also click on the charts option. That was this one here, and you've got some options. Here, I'm going to say, never exclude, right? I'm going to have frequencies instead of percentages. There's just some options for you here. So and I think it's just a reminder, always look at the defaults. What are the default settings in whatever statistical package you're using? Just to make sure they're what you want. Cruise down further. After I've clicked continue, I'm going to click OK, right? And then I'll see output that looks like this. Here is the frequency table for the raw variable of height. Here is then the frequency table for the standardized height variable. And as you can see here, the heights ranged from 59 to 80. Those were in inches. The frequencies have not changed. 1, 1, 2, 4, see, 1, 1, 2, 4. And if we look at the percentages, we look at where people are in this distribution. There's still a ton of people at the center here, 13, 9, and 12. That has not changed, 13, 9, and 12. None of that is any different. What has changed is the nature of the scores. If we look at this frequency table, we can see that the new range for height is negative 2.63 to positive 2.55, because we're not measuring in inches anymore. What we're measuring now is in standard deviations. And this person was 2.63 standard deviations below average. This person with 59 inches was 2.63 standard deviations below average. This person who had a raw score of 80, this one person, now has a raw score of 2.55. right? So we get a sense of that now we know for sure they are 2.55 standard deviations above average. Here, the mean was 69.67 with a standard deviation of 4.06. Here, the mean is 0 and the standard deviation is 1. Why? Because these are z-scores. And if I took the average of all these z-scores, I would get an average of 0. If I took the standard deviation of these z-scores, I would get a standard deviation of 1. And PSPP is just revealing that. What you can also choose under the charts option is you can choose histogram. And so if you have not already done this, please do that now. Go back to frequencies and choose draw histogram under this toggle. And because what will come in the output after then the frequency tables is this histogram. Here is the histogram for height, raw. Here is the histogram for height, Z. As you can see, the shape is exactly the same. All that has changed are the values down here. And so the bin widths have changed a little bit, but the frequencies aren't any different, right? And it's just the range down here that has changed. It's still the same roughly normal shape. Here's that same still rough normal shape. It's just this one has binned differently than this one. You remember our discussion of bins from a few weeks ago. Now, if I want to export my output file, because let's say I want to save this whole thing as a PDF, I can do, because this output file cannot be saved normally. If I want to refer to it later, I'm going to need to export it as a PDF. So I go here and I go File, Export, and then choose some name for your PDF file, and make sure to, from this drop-down menu down here, that you choose PDF, and then you're going to click the Save button, and that is then how you're going to save that PDF. The other thing that I would like to show you today is how you actually do this in a live PSPP file. So let's go and do that now. So here is a completely different file. This is called my student data file. It's just a different group of people where I ask them different questions. I'm just going to run through that same procedure that I did in the sample file with this new one as well. So again, I'm going to go to Analyze, and I'm going to go to Descriptive Statistics, and this time I'm going to choose the frequency command, and you'll see a pop-up menu that looks like this. And again, I'm only going to choose the mean and standard deviation to be reported. This time I'm going to choose height again, how tall are you in inches, and I'm going to use this little arrow to put it over here. And then I'm also going to choose the sleep variable. Let's see. Where is that? How many hours of sleep have you had last night? And then, as you recall from our last discussion, we had created some standardized variables. And remember, standardized variables get saved all the way at the end. So here they are all the way at the bottom of this list. Here's the z-score for height, and then the z-score for how many hours of sleep. And we did that as part of our last discussion of using PSPP. And now I'm going to click on Charts, and I'm going to, this little pop-up menu comes up, and I'm going to choose Draw Histograms, so it'll automatically create some histograms for me. So that's nice use of the frequency table. I can just use it to create some histograms for me. And then I click Continue. And so in this one output file, what I'm going to see then is I'm going to see the descriptive statistics for height, sleep, Z height, and Z sleep, as well as I'm going to see the nice histograms. And so here then is that output file. And as we can see, it gave me a nice frequency table for height. And then it gave me the descriptive statistics for height. And then it gave me this nice histogram here. And what you'll notice is, whoa, what's going on with this person here? Somebody reported only being Oh my goodness, it looks like 10 inches tall. Oh my, that may be why we have such a large standard deviation. As you recall, we had a standard deviation of 14 for height because we have this weird outlier here. So we might want to go into the data set and investigate this person's score, whether or not this person gave us a reasonable score. And oh, look at that, there it is. Somebody told us that they had a height of 5.3. My goodness. That doesn't seem right. And then we have, here is the how many hours of sleep did you get last night? Here we have, and here's that nice histogram. We can see it's kind of normal-ish. Go down here, and here's that frequency table for the standardized how tall are you. And then here we have that histogram. As you can see, the shape's not different. Z-score transformation, the shape isn't going to change. And then here is the standardized frequency table for how much sleep you get. And then here is that histogram. And as you can see, the shape is still roughly the same. The bin widths change, but it's still roughly the same as it was for sleep up above. Let's go up there and look at it again. See, something roughly normal. The shape has not changed. And if you count the number of bins, here it ranged from 2.5 to 12, my goodness. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9 bins. Go down here to the standardized sleep variable. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bins. That's why it's not exactly the same shape. If we had chosen the same number of bins for each in the histogram, they would have been identical. And if you can see, the range has now changed. And the center of this graph is at 0 because it's roughly normal-ish shaped. We end up with a peak right around 0, which is, of course, the average. And it's the same here. And that then is how you can use the PSPP to explore looking at z-scores and how the shapes of distributions don't change even if you're switching from raw scores to z-scores. The relative relationship among your participants will be preserved. The last thing I want to show my listening audience, my watching audience, before I sign off, isn't actually PSPP. It's actually how to use a z-table to start making some more interesting decisions about z-scores and really about the proportions between z-scores. Because as we can see, and we get things that are roughly normal. And in fact, I'm guessing height is probably roughly normal if we got rid of that very strange outlier of someone who told us they were only 5.3 inches. How strange is that? So you might want to go in there and delete that case. Someone who told us, ooh, there was 2 people who told us they were 5.3 and 1 person who told us they were 5.6. That's super weird. Super weird. We might want to go in there and delete those cases, or we might want to go in there and do something with them because nobody in the class is 5 inches. So that's an issue, right? Just something to think about and something that is totally permissible to do. If you realize this is a data entry error, that these people cannot actually be 5 inches tall. Right? Right. So now let's cruise over to the z-table and learn how to use a pretty good z-table to start making decisions about z-scores. And so here is how to use a z-score. And I think a z-table, right, if you're dealing with z-scores. A z-table is when you combine the concept of standardization, z-scores, with the concept of normality. Now remember, standard scores are not the same thing as normal. Normal is a shape. A normal distribution is going to have that bell-shaped curve. And a z-table is for when you're dealing with a distribution that happens to be normal, data that has that characteristic bell shape that you have also standardized. So let's use a working example that I have here to explore using a z-table, which is a table of z-scores that happen to be normally distributed. Now remember, because the z-score transformation is linear, whatever the original shape of the distribution will be the distribution shape after you transform them into z-scores. So the z-table that we're going to learn about now is for when data is already normal and then you have standardized. So here's my example. Let's say a couples researcher is measuring how satisfied people are with their relationships on a scale of 1 to 8. she gathers data from 144 people, so Big Mama N is 144. Her participant satisfaction ratings are normally distributed. That's important. I'm telling you that these data are normal. And so, and data is plural, isn't that fun? So it's not this data, it's these data. Ooh, the singular of data is datum. The more you know. In any case, I know that these data are normally distributed, which means it's already a bell-shaped curve. So if I turn the scores into z-scores, I can then use a z-table to start making some interesting decisions about them. So I find out that the average satisfaction is 5.5 with a standard deviation of 0.5 seconds. Excuse me, not seconds. I'm not measuring anything in seconds. Rather, this is going to be the average satisfaction rating is 5.5 with a standard deviation of 0.5. So pardon my error. We have an average of 5.5 satisfaction points with a standard deviation of 0.5 satisfaction points. So x bar equals 5.5 and s sub x equals 0.5. So we can use a standard normal table to answer some questions. I'm going to use a table called table A1, which I like a lot because it's pretty straightforward. There are a lot of different Z tables out there, and they all work pretty much the same way. But I'm going to teach you how to use the one that I have, which is titled Table A1. The first thing you're going to need to do to use any Z table is convert any raw scores into Z scores. And as a reminder, a Z score is just the raw score minus the average divided by the standard deviation. And so since I have the average and the standard deviation, I can convert any raw score into a Z score. So let's say I wanted to know the proportion of her participants between 5.25 and 5.75. Now notice one of these values is below average and one of them is above average. And so I want to know the people who are fairly close to the mean, right? 5.5 is the average. So I've got 5.25 and 5.75, but a little bit above the mean and a little bit below the mean. I want to know what proportion of people are between those two values. So the first thing I'm going to need to do in order to use a Z table to answer this question is to convert them into Z scores. So first I take the raw score, subtract the average, divide by the standard deviation to arrive at a Z score of negative 0.5. This raw score of 5.25 is half a standard deviation below average. And if we look at the standard deviation is 0.5, a quarter of a point is in fact half a standard deviation, a half of one of these below average. And it's the same thing with 5.75. Take 5.75, subtract the average, and then divide by the standard deviation. That will give us a positive 0.5 Z-score. This person with a score of 5.75 would be 1/2 of a standard deviation above average. And now I want to know, what is the proportion of people between these two Z-scores? And this is where the table is going to help us. Because I know this is normally distributed, I know that any positive Z-scores are going to be to the right of the average of 0, because Z-scores have an average of 0 always. So any positive Z-scores are going to be to the right, because that's how number lines work, and any negative Z-scores are going to be to the left of the average of 0. So the mean is going to be the center of the distribution at the peak, and then the Z-score will tell me how many standard deviations the person is above or below average. So let's say that a person had a Z-score of 0.6. I used the Z-score transformation, I subtracted the average, and then I divided by the standard deviation. I would know that that person is 0.6 standard deviations above average. And here then is what the Z-table would tell me. The first column asks me what the Z is. In my case, my Z is 0.6. The second column tells me the percentage of people from the average of 0 to that Z-score. So in this case, if someone says, I got a Z-score of 0.6, then I would know about 22.57% of people are between the average of 0 and their Z-score of 0.6. That's what the second column tells me, and that is called the mean to Z. The third column tells me the percentage of people either higher if it's a positive z-score or lower if it's a negative z-score in the tail. Because remember, this is the peak of a normal distribution, and this is the upper tail, and this is the lower tail. And so then what the third column tells you is the percent in the tail beyond the z-score. So if it's a positive 0.6, 27.43% of the folks would be above 0.6. If this was a negative 0.6, because the normal distribution is symmetrical, 0.6 negative 0.6 would be just as far away as positive 0.6. They would mirror image each other. Then I would know 27.43% would be below negative 0.6. That's how you interpret a z-table like this. So let's say I wanted to know then, and so notice something else, that 22.57 plus 27.43 will add up to 50%. Because this is the first column is essentially telling you the percentage from the average of 0. Because remember, z-scores have an average of 0. So the peak is always going to be 0 to that z-score of 0.6. Then this second column is going to be anything beyond that z-score. So this area plus this area is always going to add up to half. And then you can use the same column to make the same decisions about a negative z-score. This would be the exact same truth about a negative z-score as well. It's just the whole normal distribution would be flipped. Exactly 22.57% of the folks would be between a mean of 0 and a score of negative 0.6. And exactly a percentage of 27.43 would be from negative 0.6 and then beyond. Negative 0.6 and beyond. So then how do I apply this to the problem above? I wanted to know the proportion of people between a z-score of positive 5 and a z-score of negative 5. So let's visualize what that is. Here is that normal distribution. Got one peak and two tails, upper tail, lower tail. The average of z-scores is always 0, which means positive 0.5 is going to be to the right, and negative 0.5 is going to be then to the left. So I'm going to find 0.5 on my z-table. Here's that z of 0.5. This column to the right tells me the percentage of folks between the average of 0 and 0.5. And what it tells me is it's 19.15%, right? And so I can convert that to a proportion by simply moving the decimal place over twice. So go from here to here, boop, and then from here to here, boop, to get a proportion of 0.1915. A percentage of 19.15% is a proportion of 0.1915. So wait, let's back up. What does that mean? That means a person who has a score of 0.5, about 19%, or a proportion of 0.19 of the folks, will be between the average of 0 and their score of 0.5. That's the area in here. That's the proportion of this graph. About 19% of all the scores on a bell-shaped curve on a normal distribution will be between the average of 0 and a z-score of 1/2, about 1/2 of a standard deviation. And then the same thing will be true for negative 0.5, about 19.15%, or a proportion of 0.1915 will be between the average of 0 and the z-score of negative 0.5. So if I want to know this whole area, what am I going to do? Add. I'm just going to add them together. So the total proportion of people between a score of positive 0.5 and negative 0.5 is going to be 0.1915 plus 0.1915, so a total of 0.383 proportion. So if we look at this graph, yeah, about just over a third of all the people are in here. Just over a third of all the people are between a score of positive 0.5 z-scores and negative 0.5 z-scores. And remember, a z-score tells you how many standard deviations someone is above or below the average. So about 38% or 0.38, a proportion of 0.383, you're just moving the decimal point over twice to go from a percentage to a proportion. That's it. About 38% or 0.38 proportion is going to be within half a standard deviation above and half a standard deviation below. And just reality check it. Does that look like about 38%? Yep, it sure looks like 38% to me, right? Is right in here. 38% of the people are within half a standard deviation of the average, or a proportion of 0.383. And so let's do the same thing then with two raw scores that are not exactly the same distance from the average. Let's look at the proportion of people between 4.75 and 6.75. Notice that this is above the average of 5.5, because again, our average was 5.5. This person is below the average of 5.5. So the first thing I'm going to need to do is convert them into z-scores. So I do that. A raw score of 4.75 is a z-score of negative 1.5. Negative 1.5. This person is 1.5 standard deviations below average. 6.75 is 2.5 standard deviations above average. So then I use the mean to z, that second column here, right? Ooh, sorry. I'm going to find the z-score of 1.5 and 2.5 on here, and then find this percentage in the mean to z. And what I pull off the graph is that there's a mean to z of 1.5 of 43.37. Now again, I don't need a negative z-score. I can just look up the mean to z for positive 1.5, and that mean to z will be exactly the same for negative 1.5. So I look it up and I find that it is 43.32%. I do the same thing for 2.5. And because negative 1.5 is below the average and positive 2.5 is above the average, if I want another proportion between them, I'm going to add those two proportions together. And so let me draw that for you. So I've already been told this is a normal distribution. So here is that normal distribution. Here then is the average of 0. Because I'm converting everything to z-scores, the average is now going to be 0, right? Negative 1.5 is going to be way over here. Negative 1.5, because these have been turned into z-scores, right? Above here is where positive 2.5 is going to be. And so I want to know, I'm being asked, how much of the people are in this whole area here? Well, the z table will tell me for 2.5, the proportion is 49.38%, or the percentage. I convert that to a proportion and I get 0.4938 by moving the decimal place over twice. For negative 1.5, again, you just have to find positive 1.5 and find the mean to z, and the mean to z will tell you it's 0.4332 if you convert it to a proportion. The table is actually going to tell you it's 43.32%, the mean to z, but the mean to a negative z of 1.5 is 43.32%, convert to a proportion. So this whole area in between negative 1.5 and positive 2.5, this whole area that I'm shading in is going to represent about 0.927 proportion, or 92.7%. And reality check it. Does that look like almost everybody? It sure does to me. Looks like everybody to me. And so again, I'm just going to add the two proportions together because one is above the average, 2.5. One is below the average, negative 1.5. And so if I want to know the proportion between them, I'm going to add the two mean to z's. But what if I'm asked about what proportion of people are between two scores and they're on the same side of the average. Let's say I want to know the proportion of people between a raw score of 3.75, which is below average, and a raw score of 5, which is also below average. Well, the first thing I'm going to do is convert them into z-scores, which I have done here by subtracting the average from both and then dividing by the standard deviation. To get for a raw score of 3.75, a person like that would be 3.5 standard deviations below average, but a raw score of 5 is going to be a z-score of -1, 1 standard deviations below average. So again, I'm going to use that z table, look up the mean to z for 3.5, because again, for -3.5, it's exactly the same. And I discovered that 49.38% is going to be between the mean of 0, so let's look at that again, the mean of 0, and -3.5, which is way the heck out here, right? So this is negative, forgive my terrible drawing, this is -3.5. Well, where is -1? Ooh, it's on the same side of the average. So -1, -3.5, it's right here, right? And what I'm being asked about is the proportion of people between here, right? Between -1 and 3.5. So the mean to z from 0 to -1 is this area in yellow. But I'm not being asked about the area in yellow. I'm not being asked about the area from -1 to -3.5. Well, I see that the mean to z from 0 all the way to -3.5 is 49.98%. So in here is 34%. This whole area here, the yellow area plus the purple area, that whole area is 49%. So if I only want to know about the purple area, and I know the whole thing, purple plus yellow is 49, and I know just the yellow area is 34. If I want to know just the purple area, I'm going to subtract. If I want to know the proportion between two values that are on the same side of the average, I'm going to subtract the mean to z's to find out this little purple area here. So I take the converted percentage of the proportion of 0.4998, subtract the converted percentage, the proportion of 0.3413 to get a proportion of 0.1585, or around 16%. Around 16% is between -1 and -3.5 z-scores. What if I'm asked something like this? What proportion of my participants is just above 6.5? Reports relationship satisfaction of like crazy high, right? Crazy high, above 6.5, a raw score of 6.5. Well, again, the first thing I'm going to need to do is convert that to a z-score. Take 6.5, subtract the average, divide by the standard deviation to get a z-score of +2. Well, now, if I want to know just above this positive score, I can use that percent in tail. I can use that percent in tail over here. That percent in tail. So I'm going to find the z-score on the table, the z-score of 2 on the table, which is, I'm using a great z-table. Whatever z-table you may be using may look a little different. You're going to find that z-table on your, that z-score on your table, and then you're going to look for some percent in the tail. For me, it's a nice column called percent in tail. And I see that the percent in tail for 2 is 2.28%. So let me draw that for you. So again, this is a normal distribution. If this is the average of 0, because 0 is always the average of z-scores, if 2 is over here above average, then if I want to know just the people above here, the people beyond the z-score, then I'm going to use that percent in tail, And according to my z-score, my z-table, the percent in tail beyond a z-score of 2 is 2.28%. I convert that to a proportion by moving the decimal place the decimal place over twice, not 0.2, but over once again to 0.0228. That is the proportion, or just over 2%. You can see what a tiny little proportion that is. Only a tiny proportion of people are going to be above a z-score of 2. And if I wanted to know exactly how many people that was, I would take the total sample size of 144, and I would just multiply it by that proportion, because that's what a proportion is, right? A proportion tells you how much of this data would be in this area, right? A percentage says if there's if just over 2% of the folks are going to be above this score, well, how many people is that? If you start with a total of 144, I started with 144 people. I multiplied that by the proportion to get 3.28 people, or round to a whole number because you can't have fractional people. To get about 3 people would have a satisfaction score above a z-score of 2. The last thing to think about is what about standard error? If we're going to actually do a null hypothesis significance test and we're thinking about standard error, if the nature of the population is the same as the nature of the sample, what would our estimated standard error be? Well, remember, standard error is sigma over the square root of n. So if we assume sigma is the same as our sample standard deviation, that will be 0.5 over the square root of 144, or in this case, 0.5 over 12. So standard error would be 0.04. If we take it a step further and ask, well, then if I was doing a null hypothesis significance test, what would my raw critical values be if I was using an alpha of 0.05? And to refresh your memory, for those who've had null hypothesis significance testing, a sampling distribution of the mean is always going to be normal, and you're going to have an infinite number of averages. And so here is then the average. And the average, remember, was 5.5. So if our standard error is 0.04, then one standard error above the average, so nature of normality, would be 0.54. 2 standard errors above the average would be 5.58. 1 standard deviation below the average would be 5.46. You see here, where is my draw? So 5.46. 5.46, and then yet another standard deviation below, a standard error below that would be 5.42. Now remember, if I'm using an alpha of 0.05, that means I'm saying my area of rejection is here and my area of rejection is here, because about 95% of all the cases will be between 2 standard errors, right? So anything left over is 5%. So the raw critical values would be 5.58 and 5.42. Those would be my 2 raw critical values, right? Because that cuts off the alpha up here and cuts off the alpha down here. Of course, it only works for two-tailed tests if you're using an alpha of 0.05. And that's it. That's all I have for you today. Thank you very much for taking this journey with me beyond PSPP, learning how to think about Z tables as well. This is Dr. Jennifer Moses signing off.